Hey students, in this video we're going to go over how to calculate reaction rate and how to calculate the average rate of the reaction. So first off, when we talk about reaction rate, we usually look at it in terms of concentration. So we're going to take the change in concentration of our reactant or our product per unit of time. And so depending on the data that's provided, it's going to be in seconds or minutes or hours or, whatever. It just depends on the data. Now, when you're looking at the concentration, when we say concentration over time, we're usually going to use brackets around our substances. And when you see brackets, that means concentration. So when you see this bracket A over here, that means the concentration of substance A, okay? Our concentration is in molarity, which again is moles over liters. So this is what our reaction rate formula would look like, where you can see that it's the change in delta, means change in concentration of A over the change in time. Now, when we're talking about reactants versus products, with a reactant, we're going to put a negative sign in front of the change in concentration because reactants are going to be disappearing over time. If it's a product, we're not going to put that negative sign. We're going to leave it positive because products are going to have a rate of appearance. Okay. So when we look at reaction rates, we can be given data in different forms. We can be looking at this graph here, and this shows us reaction rates of 3 different substances in this formula, NO2, NO, and O2. So here's our reaction, the decay of nitrogen dioxide, forming nitrogen monoxide and oxygen gas. Now, when you look at this graph, we know that that green line is going to represent the NO2 because we're starting with some of that. We always start with some reactants. So you can see that the line for the the NO2, we start all the way up here with some kind of given concentration of NO2, but the blue and pink lines start down here at 0. They start at 0 because those are our products, and we don't start with any products. So you can see that the green line is coming down and it's decreasing because the NO2 is going to disappear over time, whereas the blue and the pink lines are both increasing because they are going to be appearing over time. Now, you do notice that they don't appear at the same rates, and that goes back to our balanced chemical equation. The coefficient of nitrogen monoxide is 2, but the coefficient of oxygen gas is 1. So nitrogen monoxide appears twice as quickly as the oxygen. That's why the NO line, this blue line, is all the way up here, but the O2 line, this pink line, is down here. So let's look and see how these calculations are going to go for us. So this reaction here shows us the decomposition of hydrogen peroxide. Okay, so we have H2O2 yielding water and oxygen gas. This problem gives us a table with our time in minutes and our concentration of H2O2 represented over here. And it asks us, what's the average rate of disappearance of hydrogen peroxide over the time period from 0 to 434? So again, we're going to have the change in the concentration of H2O2 on the top and the change in time on the bottom. We're going to put this negative sign here because H2O2 is a reactant and it's going to disappear. Okay, so if it's a reactant, we put that negative sign. Now we're talking about the time period from 0 to 434 seconds. So this is our set of data that we're concerned with. So we need to take our change in concentration, so 5.66 times 10 to the negative 2 minus 9.12 times 10 to the negative 2, and then our change in time, which is 434 minus 0. So that's going to give us 7.97 times 10 to the negative 5th. Now, really watch how you input this into your calculator, though, because if you don't put this top part in parentheses, like if you don't use a parentheses in your calculator, and you just do 5.66 times 10 to the negative 2 minus 9.12 times 10 to the negative 2, and then you put your divide sign, your calculator is going to divide first and then subtract that from the 5.66 times 10 to the negative 2. So it's really important to remember the order of operations in your calculator. Okay, so either do the subtracting first and then enter and then divide, or put the subtraction piece in parentheses so that way you can end up making sure that you're subtracting and then you're dividing. Okay, so our answer for this one is going to be 7.97 times 10 to the negative fifth. And our units are moles over liters times minutes. Moles over liters is our unit of concentration, and then minutes is our time. Clear this. Okay. So then here it says, for the decomposition of hydrogen peroxide, so same reaction, the average rate of disappearance of the hydrogen peroxide over time is 8.08 times 10 to the negative fifth. And then it's asking us for the rate of appearance. So again, this 8.08 represents the change in concentration of the H2O2. But we're trying to find the rate of appearance of the oxygen gas. And going back to our reaction, we can see that they have different coefficients. So we have to change this so that it reflects our answer is about the concentration of the oxygen gas. So we're going to have our moles of oxygen on the top, just like our stoichiometry or any kind of conversions. What we want goes on the top. What we're starting with, in this case, the O2 or the H2O2, that coefficient is going to go on the bottom. So we're going to multiply this by a half because the oxygen appears half as quickly as the hydrogen peroxide disappears. So that's why our answer here is 4.04 times 10 to the negative fifth. So then let's look at this reaction. We've got ammonia plus oxygen yielding nitrogen monoxide and water. So it gives us the initial concentration of NH3, our time period, and a final concentration. So first off, we want to find the rate of consumption of the ammonia. So our rate is going to be equal to our change in concentration. And now because this is disappearing, we're going to put a negative sign here. We've got 2.560 minus 4.00. And then our time period is 25 seconds. So I want you to input this into your calculators and make sure that you're going to get the same answer as me, because you don't want to make a calculator error and end up with something else because your calculator did order of operations differently than what you intended. You should be getting 0.0576. And that's going to be moles per liters times seconds, because we're talking about seconds here. So it's asking how much O2 is going to be consumed after 25 seconds. So let's look at how much ammonia was consumed. So the 2.560 minus 4. That's going to give us how much ammonia was consumed, but we want to get this into oxygen. So remember, we put our moles of ammonia down here, the one that we're trying to get rid of down here, so that we're left with our moles of oxygen on the top. Now I'm not dividing it by my time because it's asking for the concentration here. So negative 2.560 minus 4 times 5 divided by 4. And so we have 1.8 molar, our concentration of O2 has been consumed. So our rate, remember our rate, we're going to take that change in concentration, that's how much is consumed. So we don't have to subtract that from anything here, over our time, our 25 seconds, and we would get 0.072 moles over liters times seconds. How much H2O would be present after 25 seconds? So again, we can use our mole ratio. So this 0.072, oh wait, we don't want to use that. We're talking about how much, so that's our concentration. So let me just erase this. I'm going to go back up and use my concentration of the O2. So that's how much O2 I have. So I can change this and have my O2 on the bottom, and then my H2O up here on the top. And this will give me how much O2 has appeared, which is 2.16. And then my rate is going to be my 2.16 divided by my 25 seconds. And this is going to give me the rate at which the H2O appears. That's going to be moles over liters times seconds. Okay. Now I know that this says end of video 1, but I forgot to change that. So we're just going to keep on going. There's a couple of practice problems here we can look at. All right, so here I have a reaction for the decomposition of dinitrogen pentoxide. It says, suppose that at a certain moment during decomposition, N2O5 is disappearing at a rate of 2.5 times 10 to the negative 6. At what rate is NO2 appearing? So when it gives you the rate of appearance or disappearance of one thing, you can use that rate, which is 2.5 times 10 to the negative 6. And we can use our coefficients from the chemical reaction. So what should we put on the bottom here? Our moles of dinitrogen pentoxide, because that's what the 2.5 times 10 to the negative 6 is referring to currently. We're trying to find out the rate of appearance of the NO, so we put the coefficient of the NO2 up here, like this, and then we can go ahead and calculate. So that times 4 divided by 2. So our rate of appearance of the NO2 is going to be 5.0 times 10 to the negative 6. And then one more practice. So we have a graph that represents the decomposition of sucrose. Determine the rate of change of the sucrose over the course of the first 2.5 hours. So I'm trying to find my tool here. I'm going to answer it up here to show my work up here. So my rate is going to be equal to, because this is disappearing, I'm going to put my negative sign. My rate of disappearance over the first 2.5 hours. So 2.5 hours, it's right here at about 0.03. And it started at about 0.05. And we have a time of 2.5 hours. So our answer here would be a rate of 2.48. Oops, that's why. I accidentally pushed subtract instead of divide. And that'll change things quite a bit. So 0.02 divided by 2.5. That's better. 0.008. And that's going to be moles per liter hour. What would the concentration of the fructose be after 8 hours? So now we don't want to just use the one that we just calculated because that's over 2.5 hours. We want to look at the 8 hours, and this is for sucrose. And you can see in our reaction, it's a 1-to-1 ratio. So the rate at which the sucrose disappears is going to be the same as the rate of the fructose appearing. Oh, it asks for a concentration first off for B. So let's find a change in concentration here. So we end up with, after 8 hours, 0.01. And we started with 0.05. So our concentration of the fructose is going to be 0.04 because that's how much of the sucrose disappeared. And it's a 1-to-1 ratio. So that's going to be how much fructose appeared. And then to get its rate of appearance, because that's over 8 hours, we're going to take our 0.04 and divide it by 8. And I don't know why I had to do that in my calculator. I should have been able to get that. And that's going to be moles over liters times hours. moles. So that's how we calculate our average rate. If there's any questions about that, just let me know and I can help you guys out. Okay, thanks.